I'll let you guys get started. So first of all, hopefully you remember this from, I guess it's been about a whole week, maybe a little bit more. A parametric is an equation in which both x and y are dependent variables. Do you guys remember from last time when we did all the graphing exercises, x and y both depended on what? T, or time. Yep. So often we'll think of t as a time variable. As you guys saw last time, occasionally or frequently, the graph of these parametric functions will not pass the vertical line test. So y will not be a function of x in those cases, but y will always be a function of t. X will always be a function of t, simply because for every time, there can only be one x coordinate, and there can be only one y coordinate, but you could get repeats of those depending on what the time is. You guys saw that? You remember that last time, how we got the squiggly graph that kind of worked its way up? If you don't forget that, guess what you get to do today? More graphing. So you'll eventually remember it. For the next 4 examples, I want you guys to make a table of values and try to sketch the curve based on the table of values. Make sure you also indicate the direction that your graph is going. Just use little arrows for that. And then once you've done that, we will work on eliminating the parameter and we'll compare it to our graph. Just to let you guys know, eliminating the parameter is not something that always works. It's going to be something today when you look at it on some of these, you're going to be like, oh my gosh. In some situations, that would be a whole lot easier to do it that way. And sometimes you can definitely do that. Other times you either can't or it's going to make it worse. So be balanced. Don't just say, I'll just do it that way only. Try to be as balanced as you can. So if you guys would, will you please try to make the table for number 1 and graph number 1. Okay, I'm just going to kind of work independently with you here, and we'll compare our graphs and see how they go. We're just literally making a table. T is what it is. X's and Y's are going to be the outputs for the T. So let me scroll it so you guys can see.
Is there a reason why the T's go from -1, -2, 0, 1, 2, 3?
Probably should be -2, -1, I guess. Although there's no rhyme or reason that says they have to go, if it really is a time, that makes sense, but yeah. Who knew you were going to come to calculus and table? Anyways. What do you guys think? Do you have a similar looking graph? Any questions on the table, the graph, anything like that?
Are they not always a curve?
Not always. This looks like a line, doesn't it?
Yeah.
No. Definitely looks like a line.
Why is there
So it says up above, it says indicate the direction of your graph. So we started, if we, like as was asked about the times there, if we got the times in the correct order there, we'd be going from like upper left to lower right. So what we're going to start to think about here, do you guys remember how we did the graphs on the calculator? about how I had you guys turn the little graphing indicator into like that little ball. So it's almost like the ball was moving left and right, or all over the place, that kind of thing. We're going to try to think of this path as the path like an object took. And so clearly this object went in a linear path, but did it go from upper left to lower right, or did it go from lower right to upper left? Based on the way the time's progressed, I would say it would be that direction. Make sense? Okay. So any questions at all on this one? Okay, so then as far as eliminating the parameter goes, here's what that could look like. If I took the, see, I've got x is equal to 2t minus 1. We're going to use substitution. If I took the second one and solved for t, it would be 1 minus y equals t. Right? I'm just taking that, just taking this and rearranging it so that the t is by itself. And then I'm just going to take the 1 minus y and substitute that in for the t on the other one. So x is equal to 2 parentheses 1 minus y minus 1. So let's see here. This would be x minus 1 equals negative 2y. This would be negative 1/2 x plus 1/2 equals y. If I solve for y to get it into that familiar form, what does that look like? Yeah, slope-intercept form, linear equation. When we look back, or when you look back at your graph, does it look like that graph has a y-intercept of 1/2, roughly?
Yes.
Mine's already gone. Slope of negative 1/2, right? Looks pretty reasonable. So then when you do try to compare this with your graph, hopefully you look at it and be like, hey, it's the same thing. It's what I would expect to get if I tried to graph that linear equation. I would think that I would get a line that would be just like that line segment for the particular domain that I've got. Okay, that makes sense? Let's do some more complicated stuff. So if you guys would, move on to number 5. 2. 5, where'd that come from? I don't know. Okay, so same deal. X equals root t, y equals t plus 1. You've got a domain for your t's. The goal here is to find the outputs for the x's and the y's. And again, I'm just going to kind of work quietly here while you guys work on that as well. Bless you. So as you start to work on your graph, feel free to compare with mine. Eliminating the parameter on this one's pretty easy. If you haven't tried it already, you should. disappointed they didn't get the cucumber water? I can't do that water. Like, I have to just do water.
Yeah.
I can't do like the slightly flavored water.
I like the cucumber and I like the ginger.
Never had that.
I like the cantaloupe, but I can't do anything else.
Cantaloupe might be good.
They have today was the lemon lime one, and it looked like lemonade, but it looks like lemonade because it just squeezed so much lime and it tasted so bad. It was just drinking. The lemon lime water works.
Yeah, no, so,
I like the watermelon.
isn't like watermelon like mint or something?
Okay, what do you guys think?
Cantaloupe.
Did you guys, when you eliminated the parameter, did you guys get a parabola? Y equals x squared plus 1?
Yes.
And so can you see how our graph actually agrees with that?
Yes.
But it's only half the parabola. How could we get the other half the parabola?
Negative T's.
It's going to be interesting if we had negative t's. Wouldn't we have an issue?
Yeah.
Because we'd have to do the square root of all those negatives.
That's true.
Kind of by the nature of this, we're only going to get kind of the right half of it. So anyway, any questions? Okay, we're doing this by hand. Won't be often that we do this by hand, but hopefully this will help you understand a little bit about what's going on. So if you guys would, move on to number 3.
That sounds like personal.
On the, like from negative 2 to 3, or is that?
Sorry, yeah, so this is your domain is right here. The negative 2 to 3 is your domain. Hey, Josiah just asked a good question. I think it would be worth me pointing out to all of you. I'm going to highlight in an orange here. That's your domain. The y equation is just t over 2. I'm just going to go with integer values here for my domain. You can choose to do otherwise if you want. guys getting sort of a sideways parabola looking thing? Yeah? Okay. Notice I've indicated the direction of motion based on the ordering of the t's there. You should get something like this. One thing I want to bring out is what we're going to start. So far we've done no calculus. All we've done here is just what does the graph look like, where does it come from, that sort of thing. I just want to let you guys know some of the things that we'll do with these. We will, just like we've done in the past, we'll be looking for, say, like the equation of a tangent line to a graph like this. And so, we might say our point of tangency is over here, and so here is my tangent line, something like that. We could find the equation of that tangent line. We could find the slope of the curve. We could also do this. Like, what if I asked you, for how many times does this graph have a vertical tangent line? What would you say? Just one. Isn't it that far left edge? So we could draw in a vertical tangent line right about there. We could find horizontal tangent lines, maybe not for this one, but for other ones. We'll just be doing, really honestly, all the regular calculus stuff. It's just a question of how do we get there. Okay. Any questions on this one? Do you guys eliminate the parameter? So I'll do that real quick. I guess I haven't done that yet. So let's see here. I guess it would be 2y equals t. So it would be x equals 2y quantity squared minus 2. So it would be 4y squared minus 2. It's one of those sideways parabolas. Anyways. Okay. Questions? I think there's one more, isn't there? Let's take a look. Yes. So this one might challenge your unit circle skills a little bit. That's okay. Did I just hear you say what unit circle skills? The ones you're going to work on for the next few minutes. How about those? Okay, so anyways, give it a try. We'll kind of do the same pattern we've been doing.
Sorry, I see this
Let me grab this.
one.
I might actually this one. What? I get it. You haven't done this.
Man, it was pretty tight. The graphing, all little details are pretty close together. We'll get you +3.
The biggest one I've ever seen is it was like this big.
I think I graphed it a little off.
Looks like we
60 ounces.
looks like we mostly agree here, right?
Yeah.
That should be -1.
Like no joke.
Oh, I just messed that up.
I
But
think
then I left it.
otherwise, I think we agree.
4. Yeah.
Yeah.
I think so too.
Last day.
How's the unit circle treating you guys?
It's not treating me
Oh my goodness. I didn't either. I always do the triangles. Like when I do it, like when I'm doing cosine of pi over 6, I'm thinking to myself, all right, that's cosine of a 30, 60, 90, 32. I do the triangle thing. So
It just sticks better.
I think so. I can think of it as a process versus just a memorized list. Yeah. I wonder if I wonder if the circle format is really the best format. What if they presented it as like a table?
A unit square.
Would that be better?
The unit square.
I don't know if it's a square, but what if it was just a table? Maybe it made it worse. I don't know. It's always a circle.
I just draw it like this and I draw the geometry.
That would be, you know what? If you're doing taxicab geometry, it would be a unit square. Because in taxicab geometry, a circle is a square.
I'm not familiar with taxicab.
So taxicab geometry, you can only go in like a grid pattern to get where you want to go. Unlike Euclidean geometry, where if I want to like go towards Liz, I can just like point straight at her and then walk there. In taxicab geometry, the only way to get to Liz would be in a grid. So like, when you think about a circle is all the points equidistant from a fixed point in a plane. So in taxicab geometry, it would be the same definition, but you just can't point straight at it. You've got to do a grid. You have to go. There's all kinds of interesting things
So you can't have
you can
triangles.
do. This was from a modern. This just like came into my mind when you said unit square. I took this modern geometry class 20 years ago, and I just like taxicab geometry. Anyways, I don't remember the purpose of it, but it was interesting. You do it. You can do it. You can do it. Very true. Hey, has anybody got to the eliminate the parameter part? Do you know what it is?
A big equation. T plus sine squared t equals 1.
I think that identity comes up. I think so. But I think you can finish with something pretty good.
What is cosine of sine? Cosine of sine.
Yeah. We'll go through. How are we doing? Are we doing okay with a graph? I think have you guys double checked my table? I think I got it right. It's been at least a week since I did any unit circle anything, so. We good? Okay. What does this look like to anybody? I mean, does that remind you of anything?
No.
No. It's curvy. We know it's not a line, right? Yes.
I think that pi over 4, the t value is pi over 4.
Yeah.
Your table, the x value should be 3 plus root 2.
Oh, the pi over 4. Oh, 3 plus root 2, you're right. I think I was skipping ahead and thinking about the root 2. So let's say, no, hold on. You're talking about, and I just did it again. You're talking about this one. 3 plus, no, it's 3 plus root 2 because the 2's a cancel. Yeah.
Come on, Joseph.
That makes sense? Okay. I was mixing the 2 rows up. All right, guys, I do actually, I think this would be pretty informative for everybody. This is meant as, I don't know, in kindness for sure. If you looked at this and you thought, oh my Lord, trigonometry, I don't know if I can do that, you're going to want to brush up. The first thing we're going to do when we come back from Christmas is polar. And there is nothing more trig oriented than polar. Okay? Polar has a ton of trig in it. So you're going to want to be really good at that. Okay? You'll get some chances to practice here. Hey, as far as eliminating the parameter, this one was the toughest, but I also think this will end up being the coolest of the bunch here. So let me just rewrite these here. X is equal to 3 plus 2 cosine of t. Y equals this. Okay. So then, what can we do with this? Did you guys work on solving for t? Yes? Okay. So maybe we just do the first one, just because it's sitting right there. It'd be x minus 3 over 2 equals cosine of t, right? And then we do the inverse cosine of both sides. So you get inverse cosine of that equals t. So far it seems like it's going pretty well until you try to substitute, right? And then you're like, what in the world? And so when you try to substitute here, you get y. I'll just come over here. Y equals negative 1 plus 3 sine of the inverse cosine of x minus 3 over 2. Yeah? Just substitute it, right? I mean, I'm not saying that it looks easy. I'm just saying all we did was substitution. So far, so good? And here's where your understanding of what trig functions and inverse trig functions becomes super important. If I ask you to do the sine of something, what does that something have to be? Has to be an angle, right? Sine of some whatever it is, that whatever it is has got to be an angle, whether it's in degree form or radian form, really doesn't matter. We just know for sure that it has to be an angle. So what that means then, of course, is that this is really just another expression for an angle. And we all wish that it was like 35 degrees or pi over 7 radians or something, but that's the form we got, right? So we got to deal with it. So sine, golly, wow, what do we do? Well, let's figure out how this relationship works with this angle. So I'm going to build a triangle. Fair enough? So here's my triangle. And this triangle is going to be based on what I have in the orange box. I've got this angle here. I'm just going to label it with a little arc mark just indicating, hey, that's the angle that I'm working with. And I'm going to say, well, that angle, I have no earthly idea what the degree or the radian measure of that could possibly be. But I do know this. I've got the inverse cosine of x minus 3 over 2 describing that angle, right? That tells me that my adjacent side is x minus 3 and my hypotenuse is 2. Now, does this tell me what the measure of the angle is? Nope. Truth is, we don't care. Because what is the very next thing we're going to do once we write this angle out?
You're going to find the inverse sine.
Not the inverse sine.
Sorry, you're going to find the sine, which then you can make the inverse sine. I'm sorry.
We're not going to do any inverse sines of anything.
Well, but if you find the sine, then you do the inverse sine. Well, I mean, I guess technically you don't really have to do that.
It'll still have an x in there, right?
I'm just talking. Quit while you're ahead. Quit while you're ahead. Good, man.
Don't we?
What I'm saying is right. I'm just.
Don't we want to just do the sine of whatever that angle is?
Right.
The problem is sine is opposite over hypotenuse, and we don't have the opposite, do we?
Oh, we sort of do.
How do we find the opposite? Pythagorean theorem. Okay, so the opposite would be the square root of, what would it be, 4 minus x minus 3 squared by the Pythagorean theorem? That sound about right? That plus that squared plus that squared equals, yeah, there we go. Okay, so this is going to look worse before it gets better. So Pythagorean theorem, does that make sense? Okay, so then what I need to do is do the sine of that angle. So y equals -1 plus 3. And I got to do the opposite over the hypotenuse for that. So it's going to be opposite over hypotenuse, like so. And now can you see that for the first time the parameter is eliminated? There's no t's. Right? We've combined the two equations down into just one equation that only has y's and x's. Hardly recognizable though. So let's do a little bit of work here. Let's clear out the 2. Let's multiply everything through by 2. I don't know, I guess we could add the 1 over. Do you guys want to just add the 1 over? Let's do that. Let's go y plus 1 equals 3 square root 4 minus this over 2. But can I just multiply the 2 over now? Is that all right? So times 2. Then divide by 3. We're just doing some algebra here. I mean, at this point, we might not have any idea what we're doing, but we're just trying to get this thing into a more recognizable form because so far it's not recognizable at all. And maybe now it starts to get a little more recognizable. I've got 2/3 parentheses y plus 1 equals the square root of this whole mess. Any ideas on what we could do to get this to a more recognizable form? Square. Okay, so that would give me 4/9 times y plus 1 squared equals 4 minus x minus 3 squared. Yeah? Just looking familiar yet to anybody? Say again? Oh, you're in the right family for sure. Say again? It's not an eclipse. It's an ellipse. Oh, man. So we get this into standard form by dividing by 4. So that once I divide everything through by 4, I would get y plus 1 squared over 9. Sorry, that's totally in a bad spot there. Plus x minus 3 squared over 4 equals 1. And it totally is an eclipse. Man, reading the AP tests are so hilarious. I can tell you many times I've seen people like trying to justify a point of affliction or a point of infection. Some other stuff like that. Anyways, Eclipse is pretty, I think Eclipse is pretty good. Doink points, yes. That too. Anyways. So hey, does...
You're pretty good at the hyperboles.
Hyperboles, yeah. Eclipses and hyperboles. It's like a really over-exaggerated graph, right? Yes. Hey, when you look at the stuff we just did with the whole eliminating the parameter, can you start to see why sometimes eliminating the parameter makes it worse?
Yeah.
It would have been a lot easier just to deal with it in parametric form. Be like, hey, you know, if we were going to do the derivative, like the derivative of cosine is super easy. The derivative of sine or the integral of sine or whatever it is, really, really easy. Doing that, actually with all the trigonometry and all the algebra, quite a bit tougher. And so I do that not to say, hey guys, you're going to need to do this for a quiz or a test. I show you that simply to say, sometimes that's not better. And I think this is an example of where that's not better. it's going to be way more efficient to just leave it in parametric form than try to do the whole fancy schmancy eliminate the parameter. Fair enough? So just about any equation you can think of on the Cartesian plane can be represented with parametric, and so it can be a very, very useful thing. Let's see here. Any questions before we move on? Yes, sir.
Can you just use a trigonometric identity and not have to do all this?
Okay, so what trigonometric identity are we talking about?
You can solve for cosine t and sine t and then just say sine squared t plus cosine squared t.
Oh, okay, let's look at that.
So much easier.
I love it. I love it. Nowhere did I say this was better. Again, my point here was simply to say sometimes this is worse. Sometimes it's going to be impossible. Let's look at what you said. I like it. So he said x minus 3 over 2 equals cosine, and then the other one would be y plus 1 over 3 equals sine of t. And then you said, hey, let's square both sides. Say again?
Just with the identity sine squared plus cosine squared equals 1.
Right.
Then you can just substitute.
Right, so you're starting with this.
Yeah.
Sure. And so then you could, well, then you still got to, I guess you could look at it one way or the other. Square both sides or just plug in, right? Either way, sure. So then here you'd get x minus 3 squared over 4 plus y plus 1 squared over 9 equals 1. Yeah, definitely easier. But I would challenge this. I mean, I think of all the people in this room, all 21 of you, I think you are the only one that saw that, which is awesome. But I think that actually makes my point even stronger. Eliminating, if one of the 21 of you, like solid mathematicians, if only one of you saw that, is that really a great thing to think about? I think it'd be easier just to leave it. And of course, the goal here was to eliminate the parameter, but like that strategy was not obvious, right? It wasn't like, oh, clearly let's just do this. And so the point is, a lot of times just leaving it in parametric form for all the calculus stuff we're going to do, it's going to be better. So
we won't have
I like
to
that,
solve for or eliminate the parameter? Or
rarely, if ever.
Okay.
I just wanted to do that here so you could make a connection back to all the old stuff that you already know about. Because you all know about ellipses and eclipses. You all know about
Hyperbole.
parabolas and things like that. And you know about lines. Oh, anyway, cool. It makes it sound like some kind of scary virus or something, right? Okay. So guys, we'll take a couple minutes here. We'll take about 7 or 8 minutes here, and then we'll be done with this. So we're going to do a little calculus with this. And so we're going to be doing all the regular calculus stuff. Like I said earlier, it's just going to be a question of how do you get there. So here is, as you recognize here, probably some very obvious calculus stuff. So if you've got some curve represented by the parametric equations, x equals f of t, y equals g of t, then the slope of the curve at the point xy is given by right there. So the thing on the left is hardly shocking, dy dx, but I think that it bears some discussion. So you're going to hear me say this a bunch of times, both as we finish out this semester and as we start second semester especially. Sometimes, listen, it can be pretty confusing when we talk generally. Think about this. If I were to say the derivative, what do you think of? What comes to mind? The derivative. Could be f prime of x. Couldn't g prime of t be also the derivative? And to be honest with you, you're going to find in the second semester that r prime of theta is also a derivative. C prime of L could be another derivative, blah, 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 whatever. Like, think back to the related rates. Didn't we do things like V prime of t or dv dt? There was a V, there was no Y. I mean, those are all derivatives, right? Here's the point. If I ask you for the slope of a curve, or more specifically, the slope of the tangent line. If I ask you for the equation of the tangent line or the slope of the tangent line, I am talking about one thing, dy dx. I don't care if there are t's, r's, thetas, smiley faces. I don't really care what the variables are. If I want the slope of the tangent line, we are talking about dy dx specifically. Are you with me? You might wonder, why is he making such a big deal about this? Later on, we're going to add more layers to this. And I've seen people get confused, and they're like, wait a minute, I was looking for the slope of the tangent line, but there were only r's and thetas, so I found drd theta. Drd theta, not the slope of the tangent line. It has a meaning for sure, but it's not the slope of the tangent line. Slope of the tangent line, always dy dx. So you've seen the formula here. How does this work symbolically? It's really simplistic. Dy dx equals dy dt over dx dt. Well, so if you've got a fraction divided by another fraction, you simply copy dot flop. So this is essentially a chain rule type activity. So you'd get dy dt times dt dx. You can see how the dt's would cancel, giving you the thing that you're looking for. So dy dx is equal to dy dt over dx dt. This has always been true. We just have never looked at this in terms of parametric. So as far as formulas you need to memorize, that's one of them, for sure. But we'll use it so many times, you probably won't have to put much effort into that, but just so you know, definitely want to be able to do that. Okay, and then the other one, carefully look at this. If we're looking for a second derivative, this is where people usually stumble if they're going to stumble. Second derivative of y with respect to x. Okay, there's a lot. This is really symbolically heavy. So this right here means second derivative of y with respect to x. It's not the second derivative of y with respect to t or z or, I don't know, other stuff. It's specifically that right there. So the second derivative of y with respect to x is ddt of the first derivative divided by dx dt. And to give you just a point of comparison here, we can go a little bit deeper with this later, but to give you a point of comparison, I want to show you how it's actually very consistent with what we did before. So I'm going to start with this right here. So check this out. If dy dx, which is really this, ddx of y, if that really equals ddt of y over ddt of x, then if you can you see how, I'll put it like this. Would it be fair to say that that relationship is true? D squared y over dx squared is equal to ddx of dy dx. So what I'm going to, the parallel I'd ask you to draw here is that, do you see how this is in the same place as this? So wherever you see a y in the previous concept, you put a dy dx. So this would equal ddt of dy dx over, well, there are no y's in the denominator, so it would just be dx dt. This dx dt would be the same as that dx dt. So I thought we'd finish is with number one, okay? So if you guys would, fiddle around with this for a couple of minutes here, see if you can figure out what dy dx and d squared y over dx squared would be. And like I said, this is where we'll finish and be done for the day. And then if you haven't, if you want a few more minutes to work on the second derivative, that's fine. So dy dx equals dy dt over dx dt. So in this case, dy dt would just be 6t minus 2. And dx dt would be, what, t to the negative 1/2? Look about right? So one of the things you're going to find, this is what I wanted to kind of cut in right here. One of the things you'll find here is with these, if you do have to find a second derivative, it is going to be a whole lot easier for you to simplify that before you move on to a second derivative. And so I'm going to go ahead and do that. So this would equal 6t minus 2 times t to the 1/2. And then when I distribute this, I would get 6t to the 3/2 minus 2t to the 1/2. So just hopefully a helpful hint there. If you know you're going to be going on to find a second derivative, it would be really smart, hopefully really convenient for you to simplify your first derivative before you even think about a second derivative. Okay? So ready to go. See if you can take that and run to get your second derivative. We're supposed to do ddt of the first derivative. This notation up here looks a little bit awkward, but it's actually not that bad because dy dx is already in terms of t. So the ddt of that is going to be pretty straightforward. So ddt of dy dx would be, what, 9t to the 1/2 minus t to the negative 1/2. And then all of that is divided by dx dt, which we already had from the previous step. Dx dt is t to the negative 1/2. So technically at that point you're done. But if you wanted to, you could simplify a little bit. You could flip that t to the negative 1/2 up. And if you did that, that would give you 9t minus 1. Yeah, 9t minus 1. Okay, questions, concerns about that? So this first derivative is the same first derivative that you found like forever. The second derivative, same thing. So with the second derivative, you can tell about concavity. First derivative, you can tell if something is increasing or decreasing, et cetera, et cetera. Still the same first derivative, still the same second derivative. We're just getting them from different places. Okay, so we'll practice with that some more tomorrow.